So welcome to today's free educational webinar on combining wind and solar, the complementarity of wind and solar for optimizing levelized cost of energy in hybrid microgrids. I'm Marilyn Walker, the Chief Operating Officer here at Homer Energy, and I'm excited to be here with you today and really do appreciate you showing up. We do these educational webinars monthly, and that keeps you up to date on what's happening in the world of Homer and how to best use the Homer software and our services here. So one of the things I've been doing is inviting some of our component partners to talk about how their equipment works in Homer. And today's a collaboration between one of those partners, Xant, makers of mid-sized wind turbines. So today we have Zandt CEO Alex Abreu, who's going to introduce you to their product line. And then Homer Energy CEO Peter Lilienthal will walk through some modeling examples of how wind and solar can be complementary technologies to optimize LCOE, or levelized cost of energy. So for those of you new to Homer, it's an acronym for hybrid optimization of multiple energy resources. And the Homer approach includes 3 different processes nested together. At its core, Homer has a simulation engine that simulates the operation of an electric power system for 1 year, hour by hour, or all the way down to minute by minute. And then at each time step, Homer looks for the most cost-effective way to meet the electric load based on the set of constraints that the user defines. Simulation then tells you how one system operates, and then an optimization step simulates up to hundreds or even thousands of different systems to find the least cost system. Homer also has an option to do sensitivity analyses, and I know Peter is going to talk about this in his presentation, and these allow you to look at the impact changes in variables you don't have control over, such as fuel price or wind speed, which you won't always know perfectly, what they have on your system and your design costs. So using Homer to design and optimize your microgrid or distributed hybrid energy system has 3 main steps. First, you provide basic information on the economics, such as the interest rate, with your energy demand profiles, location, that's going to tell us the renewable resources, the solar radiation and wind speed, and then the types of equipments that you want to consider, shown here as the system components. Homer then steps through the 3 nested processes I talked about in the last slide, simulation, optimization, and sensitivity. And it provides detailed results not only on the economics of the system, but also on what's going on literally in every hour, if that's what you need to know. So we have now have 2 versions of Homer. Homer Pro is our original product and still our flagship, and it has many different choices for modeling. We also now have Homer Grid, which was designed explicitly for behind-the-meter systems in grid-connected markets, where demand charge reduction, time of use rates, maximizing self-consumption, incentives, resiliency, or some combinations of these are what matters most. And we do now model wind in both of these products. I think Peter's going to focus on Homer Pro today. Alex is going to take over and talk a bit about this mid-size wind line that they have. Okay, Alex, you're live.
Hi, Marilyn. Hi, Peter. Hi, everyone. Thanks for having me on the show. I'm very excited to present our technology to the listeners. So I'm Alex Abreu. I'm CEO of Xant. We started out about 6-7 years ago developing wind turbines specifically for these markets. So, and there I'm focusing on both the distributed energy behind the meter applications as well as specifically the off-grid markets. Wind power made easy is our slogan because what we saw in the market that wind is often perceived as complex. You know, people think it's heavy weights, it's difficult logistics, it's years and years of measurement campaigns before you can put up a wind turbine. We think things can be done differently, and so we started out developing this products portfolio where we focused on the mid-size, because these are turbines that are meant to go where, where before it was difficult to put winds, and where clearly you can get a multi-megawatt wind turbine. 50 to 500 kilowatts is the range we cover, which means we cover any energy consumption between, let's say, a few hundreds of megawatt hours per year up to a few gigawatt hours with different products. As I already mentioned, we focus on both on-site generation and off-grid systems. The key drivers of our markets are fuel and battery saving. I mean, we are competing, let's say, or the alternative to renewables and to winds is obviously using a diesel genset and burning fuel to generate electricity. But more and more, we also see that if you want to increase the amount of renewables, you have to incorporate some storage. And then combining wind and sun reduces the amount of storage needed to match your production profile with your demand. But this is the topic of the talk, so we will dive much deeper into this later. Obviously, as Marilyn already expressed, I mean, it's a hedge against, varying energy prices, electricity prices. And also in the case of wind, it can be a very interesting landmark for some of our clients who want to showcase their levels of ambition in terms of sustainability. So I'll just briefly introduce our technology. I mean, because often we see, unfortunately, we see that a lot of homer users, they do not consider winds just because of that perception of it being too complex, and too expensive. So we want to point out that there is wind technology out there that is perfectly suitable for your site, even if it's a remote site. Like, for example, here, how we show that our Xant M platform, which is a 100 kilowatt platform, completely fits into one single container. So one 40 feet container is enough to bring 100 kilowatts on site. So that ensures that this piece of equipment gets there in one piece, and obviously minimizes transport costs. The other very important aspect is once you are inside, how to install this. We think it should be a very straightforward solution where you just basically bolt pieces together. We have been compared with a typical IKEA bookshelf where you get the kit and the little key and the manual, and you just put it together yourself. We haven't quite reached that stage of development, but what we do on site is indeed bolting together the various sub-assemblies and bring it together in a very straightforward way without using any heavy equipment except for a loader. And then most importantly, once you have your turbine assembled, how to erect it. And this is where we obviously differentiate from larger machines, where we are always able to tilt up the turbine with a simple 4-ton winch, which is a very standard piece of equipment. And so this avoids bringing a crane to the site, which can be an enormous cost in some locations, or even close to impossible challenge. It has the additional advantage, of course, that if you're in a very hurricane-prone or tropical storm region, you can lower the wind turbine. In about 1 hour, the turbine can be lowered. And if your technicians on site are not certified to work at height, they can also do all the maintenance at ground level, which enormously facilitate to have your local crew trained to maintain our machines. One important aspect, and we've mentioned it, I mean, the storage, the role of storage as an enabler of increasing the renewables in these hybrid power systems. We've come up with an integrated storage part where, as we have a full power converter, we can easily integrate modules of about 50 kilowatt hours into our turbine. And this opens up a whole wide variety of applications. I mean, you could still be just delivering power to the grids, to the microgrid, but you can smoothen that power, which allows for an easier integration. Let's say you have an existing diesel system, and you don't want to upgrade the controllers of the diesel. You just want to run the system as it is, but you want to add some renewables. Providing some storage to smoothen the output capacity, to reduce the power gradients enormously will facilitate the plug-and-play integration. Now that's just one step. And then you go from there to the full other end of the spectrum, where the turbine basically becomes a virtual synchronous machine that can take over the grid forming role in case your diesel genset drops out. So storage becomes for us an integral part of our product portfolio, and we think the combination of wind and storage will allow, the easiness, will enormously increase the easiness with which renewables can be integrated into existing hybrid systems based on diesel gensets. Now, looking at the resources, and this is really the key message of this webinar, just looking at the maps, and there's two fantastic maps that exist, the Global Wind Atlas and the Global Solar Atlas, both projects financed by the World Bank. Just looking at these maps on a global scale, and obviously, knowing that the brighter colors represent higher resources, you can immediately see how geographically those two natural resources are very complementary. And then also in terms of siting in a particular application, when you move to the coasts, you often have more unperturbed, on-flowing wind speeds. So you usually get a much better resources when you move closer to the coast. The opposite is true when you go up the mountains. You will usually have a higher solar irradiance. So solar and winds are really a match made in heaven, I would say. And this is confirmed also on a time base. If you look on a time horizon, both seasonal, and these are the two top charts, and also from a diurnal pattern, you can see how on average, and it's often compared to two smiles, the wind smile is a smile that's going up. The typical curve of a PV system throughout the year is something that obviously peaks in the middle. The same is true for daily patterns, of course, and winds on a daily basis tends to be a bit higher over the nighttime, and especially the morning and evening periods when it kind of picks up in the morning and then picks up again in the evening. These are broad trends, and obviously every site you need to evaluate that, and Homer is capable of downloading the wind and solar resources on that particular location based on databases. But these broad trends confirm themselves on various on a lot of locations on Earth. So this makes really the case for combining wind and solar when you want to come to your most cost-efficient system. Out of interest, we run a few systems, actual systems that we either built or did the system engineering for, and we ran them over a range of global horizontal irradiance. We ran them over a range of wind speeds, and then looked at the solar plus storage system only, and then the solar plus storage plus wind system. So looked at the LCOE reduction when wind was added to a system, and these are all renewable systems. I mean, this is a somewhat ambitious futuristic vision. I think renewable penetration, the economic optimum of renewables penetration currently in hybrid systems is not the full 100%. But even when you want to go to higher penetration degrees and you want to keep some of that dispatchable power generation, such as the diesel genset, the conclusion is still valid. Adding wind to your system as soon as you have a site where you have a 5 meter per second average wind speed will reduce your LCOE, will reduce your levelized cost of electricity. So I'm going to conclude here. I'm just going to show some of the examples where we actually seen this in the field. This is one of our first turbines where you can see the container and the actual tilted mechanism. This is an interesting site as well. This is a near off-grid solution where the grid connection was very weak, and the community needed a higher load. So what they do is they have a 100 kilowatt wind turbine, but they can only feed 50 kilowatt back into the grid. So the other 50 kilowatt needs to be managed locally. And there they used an interesting system of dumping the energy. One system, I'll skip this system, this is Scotland as well. One system that effectively combines solar and wind is this system in Vanuatu. It's one of the Pacific Islands, where the local utility is very ambitious in its renewable targets. So we're looking forward to complete the wind farm and upgrade it with our technology. And then finally, this interesting system is, of course, the system we've recently commissioned last year in Alaska. The combination also of wind, solar, and batteries will be providing electricity, and this system will effectively run in diesel off mode most of the time. With this, I hand it over to you, Peter, and I'll be glad to take questions at the end.
Yeah, Alex, I do have some questions that have come in that are really just for you, and so I'd like to go ahead and handle those if we can. Sure. The 40-foot container, is that for all of your turbines or just specific ones?
Well, the 100 kilowatt platform can be shipped in one single container. The L, which is the 300 kilowatt platform, will be several containers.
Okay, great. Let's see, what kind of batteries are you using? And then it also says, do you have your own software or you're using someone else's? I'm not sure what they mean by that. But anyway, that's one question.
We use lithium-ion technology because we use a battery size that is both suitable for these microcycles. So we will smoothen the power output of the wind turbine, but these are very shallow cycles, and then we can do a wider range variation of state of charge. But we usually take 50 kilowatt hours as the module, and then can do several modules in parallel. In terms of software, we do have our own software, so it's actually our own software managing the state of charge of the battery and controlling both generator side and grid side converter to manage the power flow.
Great. How do you deal with icing in Alaska?
The turbines we've put up in Alaska are equipped with, first of all, black blades, so they absorb more of the solar heat. This turns out to be a quite effective, very natural de-icing system. But in addition to that, they're equipped with a blade heating system. So we blow hot air along the leading edge of the blades to de-ice the blades so they can have the maximum runtime.
Great, thank you. Okay, one more question, then we'll move on. We are getting a lot more, but this is great. So before we go to Peter, what's the average installed cost of the 100 kilowatt turbine?
Total installed cost now is about $3 per watt, depending obviously on site conditions. I mean, the soil can be quite beneficial, can be quite easy to handle a foundation, or it can be somewhat complex. But we count with about $3 per watt.
Great. Okay. Thanks. So Peter, go ahead and unmute yourself and start talking, please.
Okay, thank you, Marilyn, and thank you, Alex. Before I jump into my presentation, I'm going to answer a couple of other questions really quickly. There was a question about whether we have special academic packages. That's true. There was also a question about whether Homer Pro has grid capability, and it does. But for grid-connected projects, Homer Grid is really designed for that. So, a really good question on how many reserve days is battery sizing done for. This is one of the main purposes of the Homer software, is to answer that question, because simple rules of thumb, like you need 3 days of autonomy, will not get you the lowest cost system. It really depends on your load shape and your resource variability and a million other factors. We find that except for the very smallest systems, backup generators really help reduce the battery sizing and the overall cost, even if you don't use them very much. You don't. So the optimal system typically does have a diesel generator that's used very infrequently, but has a big impact on reducing your battery sizing. But it's very site specific, so that's why you need Homer to answer that question. The rules of thumb are just inadequate for answering that question. So let me get to my presentation, and I want to just give kind of a ground. Why are we doing all this? Well, the world needs to go through this transition from polluting power to carbon-free power. We believe that is also going to go from large power plants, which is really the only way to do coal plants. But the sun shines everywhere. The wind blows in many places. These are distributed resources, and we believe strongly that distributed power is the future, but it's different. So I have to make a pitch for why we did Homer in the first place. It's to accelerate this transition to clean distributed power. And we've been doing microgrids for 25 years, first at NREL and now independently as a private company. And just I want to give sort of an overview of the market as a whole. When we distinguish it into 4 different kinds of microgrids. Island utilities, which is probably the market that Alex is talking about mostly. These are places currently burning diesel, maybe 24/7. It's an existing utility, but it's a diesel-powered utility. It's a very expensive power. It's an off-grid or isolated utility. We distinguish that from the energy access market, which is over 1 billion people, and there's no infrastructure there. There's no existing utility. These would typically be smaller systems, but and there's all kinds of non-technical challenges. But in many, many cases, microgrids are the most cost-effective way for them to get high quality, the kind of power needed for economic development, productive uses, etc. And in many, many parts of the world, the microgrid is going to provide higher quality, more reliable power than the existing utility. So it's actually preferable to grid extensions, and it's often cheaper as well. I say that about microgrids providing high quality, reliable power because what's happening in the U.S. now is ever since Superstorm Sandy, and actually now there have been many other hurricanes, but that one sort of was the first one as a wake-up call that we needed to think more about resilience and reliability. So here in the U.S., microgrids are being developed specifically because they can provide higher quality, high reliability power, and they're not dependent on the transmission and distribution system, which is where the vast majority of outages occur. So nothing you do on the other side of the T&D system can help solve that problem. If you want to be resilient against those kind of outages, you have to have distributed power. And we're demonstrating here that these microgrids can provide that kind of high reliability power. In much of the world, it's not a question of getting high reliable power, it's getting any kind of reliable power because the utilities all over the world, people suffer utility outages on a weekly basis or more. So those folks already have backup power systems, but their diesel generators, they're noisy and they're expensive and people really hate having to run these backup generators all the time. So microgrids are a clean, quiet, lower maintenance way to back up the utility company. So and those are pretty distinct markets. So we like to think of them separately. But Homer is really designed for all 4 of those markets. So another way to break up the market is by what is the value proposition. And there's a lot on this slide. I won't go to it all, but there's 3 separate value propositions. Reliability I've talked about for critical infrastructure and emergency services. Fuel savings is the predominant one in the island market, but actually solar's gotten cheap enough, wind's gotten cheap enough, batteries are getting cheap enough, inexpensive enough to provide energy cost savings in any place that has expensive power, including places like California and Europe and Japan, etc. But where they're burning diesel, it's even more obvious. So that's the second value proposition. And finally, it's been demonstrated over and over now that you can do renewables at extremely high penetrations in a microgrid. Lots of examples now of microgrids with over 90% renewable penetration. And that's much higher than the large utilities are able to do on their systems. And a whole variety of reasons for that. So we believe that is actually going to be the largest value driver as renewable portfolio standards increase and as the global move towards cleaner power increases. this is the way to do renewables at very high penetrations. So you can look at all the different markets I've put on there, but I'm not going to go into that in a lot of detail. The other thing that we've noticed starting, like I said, 25 years ago is that there's too many choices. There's a lot of different options here. I've listed some of them here, and it's great to have a lot of options, but it's actually kind of confusing. So we created Homer to help you figure out what is best, and the answer, unfortunately, is that it depends. There's no cookie cutter, one size fits all solution, sort of like the way the Model T created the car industry back 100 years ago. Unfortunately, we have this flexibility in the design, which is good, but it's kind of confusing because the answer of what's best really depends on what are your local resources, what are your energy requirements, the load shape, daily, seasonal reliability requirements, opportunities for load management, all really affect the system design. And the technology keeps getting better, which is great. Prices are coming down, performance is improving. That's fantastic, but it actually does add to this confusion about what's the best solution. That's changing over time. And what I learned a long time ago is that a confused mind says no. So our job is to help fit those pieces together so people can feel confident that they're making the right decisions. The other thing that's become real obvious as we look around the world and at the people trying to develop these projects is that you've got a lot of different parties at the table. You have renewable advocates that want to talk about 100% renewable systems, and you have diesel mechanics who are scared to death of talk like that. These folks, it's really Mars and Venus. These folks aren't talking the same language. Likewise, you have power engineers that have very sophisticated engineering tools for things like transient stability, load flow, et cetera, power quality issues. Those very sophisticated tools don't consider economics at all. And you have the finance community that have their spreadsheets that don't consider the technical solutions. And if you want to develop a project, you need all four of those people sitting together at a table, speaking a common language, agreeing on all the different issues that come up. We've created Homer as a tool that sits in the middle there. It doesn't handle transient stability, and it doesn't handle all the different financing structures. It's something that all four of these groups can work with to bridge their different worlds and communicate effectively with each other, because the project's not going to get built until all four of these people agree it's a good project. All four of these types of people. So Marilyn gave a background on Homer, and I'm just going to have this one last slide here on like I say, we've been doing this for 25 years, starting at NREL. At this point, over 250,000 people have used Homer, so it's become a de facto standard for microgrid design. We put out a newsletter. I guess you all probably get it because that's how you're stuck on this. There's 90,000 people. So it shows a couple of things. One, how much global interest there is in microgrids. You can see from the map kind of where the interest is greater. In a place like the Philippines, the dots are all on top of each other, so you can't really underestimate that. And I'm going to move along to talk about the Homer analysis that we've done with the Zandt turbine. And we did two. We did one analysis in Ambon, Indonesia. This is a community, a peak load of 247 kilowatts. We did a sensitivity analysis. So this graph needs a little explanation, but the x-axis is the capital cost of the Zandt turbine. And Alex says that if there's no logistical challenges, you can install one of their turbines for $300,000, a 100 kilowatt turbine for $300,000. That's a total installed cost, including shipping, installation, all the logistics. So Homer requires that total installed cost. Now, if you've got logistic problems, challenges, and there's all kinds of situations where the total cost might increase. So that's the x-axis, and the y-axis is the average annual wind speed. So I took wind data I had for this island in Indonesia, and Homer gets that from a global database. Wind is very site-specific. We always recommend that you do a sensitivity analysis on the wind speed to see how much it matters, because the wind in your specific location might be a little different than wherever you're getting your data from. What's dramatic about this graph is how cost effective these wind turbines are, even in modest wind resources. So the red portion of the graph is where wind is not cost effective. If it's down at 4 meters per second, it's really not going to be cost effective. But as soon as, even if at 5 meters per second, it becomes cost effective. And the numbers on the graph are the levelized cost of energy. So the PV only system in this case has a levelized cost of energy of 32.6 cents. And as you move up into better wind resources, you can see that that price goes down quite dramatically to as low as 21.8 cents. We were talking with Alex before the start here, and some of his sites have wind speeds, average annual wind speeds of greater than 10 meters per second. That is actually quite unusual. But the conventional wisdom in the large utility scale wind world is that you need at least 7 meters per second, really. But in this small size where you're competing with diesel, you can go down to 5 meters per second, and it still provides a reduction in the cost of energy. Likewise, I'm not going to show all the graphs and all the numbers. I'd kind of overwhelm you. But at the same time, it's also substantially reducing your diesel runtime, substantially reducing your battery sizing, and your overall capital costs. So that's in a tropical location that doesn't have a lot of seasonal variation. I'm going to talk about another analysis that we did in Crete, an island off of Greece, to show the value of diversity. So solar diversity is always good, just in general. And it adds to reliability and resilience, and they can complement each other, they can smooth each other out. It adds to reliability, because if something's down for maintenance, the other resource can play a role. And as Alex mentioned, the sun obviously is highest in the middle of the day, but wind produces 24 hours, and in many places, those evening loads are usually the highest. The solar can't contribute to that except through the batteries, but the wind can contribute directly to those peak evening loads. And likewise, in much of the world, the wind is strongest in the winter and the sun is strongest in the solar, so that's a seasonal variation. And, you do have clouds and you do have, gusts and lulls in the wind, and they're uncorrelated with each other, so they balance each other out, balance those random variations out as well. So we demonstrate that with this analysis that we did in Crete. We demonstrate some of this with this one graph here, where you can see that February, the PV output is lowest, but the wind is higher. And then in May and June, the wind dies off a bit, but the solar picks up. Crete happens to have also a secondary windy season in July and August. So in July, between the good solar resource and the good wind resource, there's almost no diesel usage at all. So this is the kind of complementarity that really varies from place to place, and really is one of the big reasons why running Homer with site-specific data gives you better answers. So just to wrap up my portion here, and we can get to the questions and answers. So why wind? Well, solar has capacity factors of 20%-ish. That's pretty good for solar. You can get maybe a little higher, and then I know they're putting solar in the UK and getting even much lower capacity factors. But wind can often have capacities of factors of 30% or more. So that's a really important factor when you're comparing technologies, because it justifies a higher capital cost if you're getting a higher capacity factor out of it. I already mentioned the evening production, but it's worth reiterating, just because that is when the peak loads occur, is after the sun sets. And I've demonstrated the lower cost of energy that you can get in good wind regimes. Altogether, you can get to much higher renewable penetrations with a combination of solar and wind than you can with solar by itself. So that concludes my portion of the presentation, and I'm sure Marilyn has been collecting all these questions for us. So I'll pass it off to Marilyn to fire away your questions at us.
Okay, thanks, Peter. So yes, we have a lot of questions, and we'll get to as many as we can. We have some time, so that's great. So I'll just start kind of back at the beginning. What are the functions that are supported by the Zandt wind turbines and battery storage? Does it support like voltage, frequency, support reactive power, etc.?
Yeah, we can actually do reactive power control without the battery even. I mean, we have some leftover capacity on the grid side converter, so we can do VAR control or, provide VARs on demand or even do local voltage control. If we add the battery, then we can do primary reserve. We can, boost the output or reduce the output as a function of frequency and actually help not only stabilize the grid voltage, but also the grid frequency.
Okay. How about the ranges of wind speeds? I don't know if you covered that earlier or not, but we have a question on that.
Well, ranges of wind speeds, we can, I don't know what exactly is the question, because we can install wind turbines at sites, as Peter said, it starts to become, very cost efficient and interesting at 5 meters per second, and then up to 10 meters per second average wind speeds, which are very extreme sites. Does that answer the question?
Yes, that is the exact question, is what are, and I would think that would mean really the upper range of it. Yeah. Is Zandt planning on pursuing any small wind turbine certification in the U.S.?
We're looking into the U.S. We have installations in Alaska, not yet in the lower 48. We have an IEC certification done by TÜV, one of the German certification bodies. We're looking into it. We haven't decided yet.
Okay, and not sure, this question could go to either one of you, I think, but for conventional grid-connected applications, I mean, we have had requests, I know, to put wind into Homer Grid, and we have done that because we do know that we have some developers here in the U.S. that use wind for their commercial industrial grid-connected applications. Do you know of any that, can you talk about Zandt in grid-connected systems?
Yeah, like I said, this is also one of the markets, and it's potentially at this time a bigger market, the behind-the-meter applications. We see a lot of opportunity in warehouses, cold storage often, because they have a demand that can be somewhat controlled or at least delayed. Any place effectively where there is a constraint in footprints, because we don't take a lot of space on the ground, just a few meters in diameter for the tower, and where you can have a hub height that comes a bit above your surrounding buildings, makes an interesting case. And again, starting at 5 meters per second wind speeds, we can do a feasibility calculation and usually come to a levelized cost of electricity that's well below the price you're paying from your local electricity provider, and this is where your revenues come in. Okay.
Do you have any projects in West Africa? Do you know if your product's been used there?
We have, we're participating in a tender in West Africa, and I'm so glad to tell that we've won it. We are working on the financing, and this is in Mauritania, for off-grid locations along the Mauritanian coast. Excellent wind resources, and there we will use a combination of winds plus storage.
Okay. Okay, now we have a bunch of questions that are sort of general Homer questions. I try to answer those sometimes, but anyway, so Peter, these might be more for you. They could be for anyone. Does Homer simulate vehicle-to-grid?
Well, that's a great question, and we're getting more interest in that. And ironically, we were looking at that back before anyone really cared about it, back when we were still at NREL. So deep inside of Homer, there are some algorithms for vehicle-to-grid, but there just wasn't any interest in it when, in 2009, 10, 11, 14. Now that there is starting to be interest in it, it is definitely on our roadmap as something to add. There's some workarounds that you can use for it now if you're kind of creative. So if you're interested in that, talk to us and we can show you how you can use the existing Homer to model vehicle-to-grid. It's something we plan to add probably towards the end of this year. I don't want to give a definite date yet, but the interest in that, it's very interesting that the interest in that has skyrocketed in the last 6 months even.
Yeah. Okay, so we have a lot of questions. I'm going to kind of combine them. We have a lot of questions about wind data and resource data. And Alex, I wonder if either one of you actually that can talk about that, both generally like what data are available, what data are needed to do a good job with the modeling.
Well, first of all, and Peter, you please don't hesitate to complement my answer. But there's first of all the databases that are included in Homer itself. That's the first step. One other resource, one other database we like to use is the Global Wind Atlas. I already mentioned. This is a very very easy to use tool. It's a clickable map. You click on it, and then you can either put a point or an area, and you get an average wind speeds. You get a bit of a distribution, where on that location you have the absolute maximum and the minimum wind speed. And this is a fairly accurate database. Now, what we've been asked in the past is by clients, should we put up a MetMOS? Should we do a measurement campaign? What we recommend is that for a project, we're talking about a $300,000 project. I mean, putting up a MetMOS is gonna cost you, anywhere between $30,000 and $60,000, and you have to then measure for at least a significant amount of months, do a correlation with another database. I mean, you're looking at making the project much more complex to make it, at least 6 months longer, and to add 10 to 20% to the costs. For having a wind speed accuracy that reduces your uncertainty by a few percent, we don't think it's worth it. I mean, it's not a power plant wind farm where you're going to put up 20 megawatts of wind and have that bank financed. So we recommend against that. We advocate using the public available databases, and then obviously doing a site visit, chart the obstacles, and then obviously try to do a good siting where you want to stay away with your rotor from those obstacles, and adjust your hub heights to the obstacles on site.
That's a really important question. And there's such a big difference between developing a utility scale project that could be several $100 million versus a project in this size range, which is several $100,000. And for those larger projects, and I know this is sort of biasing people's thinking about the need for super accuracy. Those large projects need that super accuracy. First of all, you're dealing with a huge amount of money, and also that they're trying to have as high a leverage as possible. But in these smaller projects, you're not going to get that kind of leverage no matter what you do. And I agree with Alex that these existing wind data sources, and there's other ones. For example, 3Tier was recently bought by Vaisala. They sell wind data. AWS True Power was recently bought by Underwriters Laboratory. These are places they will help you get much better data without putting up a Met tower. But those are paid products. But this is why we think sensitivity analysis is so important, because to find out, well, what is the threshold that makes this project cost effective? And let's say it's 5.5 meters per second, and you've got data suggesting, oh, this is probably 7 meters per second. There's a fair amount of uncertainty about that, but it's well above the threshold to make the project cost effective. So that is why we've designed Homer around making it easy to do this kind of sensitivity analysis.
Great. How about figuring out the operating cost for Zandt turbines?
So, yeah, wind power made easy. So we've stripped it down. We've stripped down wind turbines to the bare essentials. So there's no pitch control. There's no gearbox. There is a passive yaw. I haven't talked about that, but this is actually a downwind turbine. So the rotor will kind of align itself when the wind is picking up. So we saw a way of increasing the reliability by taking out the most failure-prone components, which also means that the amount of necessary servicing is reduced. So a one-day visit to the sites sufficient in the case of a Xant turbine. So what we usually do is we train our local partners. We operate on a global scale, so for us it makes no sense at all to organize service from our headquarters, but we rather give the tools, the manuals, and the training to our local people.
And I want to reinforce just how valuable tilt-up, tilt-down towers are for a whole bunch of issues, including erection and installation, but also for maintenance. And Alex, you said 1 day visit. You mean 1 day per year? Is that what you recommend?
Yes, so 1 day per year. And if it's a tilt-up tower, yeah, you tilt it down in the morning, then your maintenance becomes indeed very easy. There's no harness to wear. There is no all kinds of safety issues that you don't have to take into account, because there's no vertical drop risk. And then in the evening, you tilt the turbine back up, and you're done.
Great. Okay. We always get this question, Peter, so I'm going to pass it over to you. Talk about reactive power in microgrids and Homer, please.
The new Homer grid does have a way to adjust for your power requirement if you have a poor power factor. Homer is fundamentally an energy analysis tool. If you have poor power factor, you need more power to provide the same load. And that's actually a very, very deep topic. And so it depends what the power factor question really is. Is it how much extra capacity do we need because of power factor issues, or what are the different ways to provide reactive power, which is more of a technical question. Actually, I'm going to pass this over to Alex, because my understanding is that the power electronics within Zandt, and actually it's becoming more and more common, and it's becoming easier and easier to get this kind of power electronics, can not just provide the extra power, but actually correct your local power factor. Is that right, Alex?
Yeah, as I mentioned before, this is a full power electronic system. So that means all the power is converted from AC to DC and back to AC, which gives you full controllability on your power factor. So we can steer that, and reactive power is a local issue. I mean, it controls your voltage at your interconnection point or along the feeder where the wind turbines are installed. So it can perfectly be handled by local voltage control algorithms, and this is what we provide. Or it could be, a centralized control system where a reactive power reference or a power factor reference is sent to the wind turbine via the power management system, and then the grid side converter will implement that power factor within the kilovar range that is allowed on the grid side converter. But the converters we use are quite, they're dimensioned for providing up to 0.9 power factor. So there is quite a bit of capacity there to help you control your microgrid voltage.
Here's a great question, and then I'm going to have you answer this question, Alex, and then I'm going to sort of wrap up on how people can get other questions answered. Does Zandt have an actual hybrid system that was validated to show performance projected by Homer?
Well, we're a wind turbine provider, so our key mission is to provide the most microgrid friendly turbine. And what we do is through partnerships with all kinds of system integrators, people that provide batteries, energy management systems, people that provide the PV component, always put the optimum puzzle together, because that's a project specific answer. Every hybrid system is different, but the wind turbine technology can be the same, or can be one of the Xant wind turbines. So we know a lot about hybrid power systems through collaborations with partners. We know that if we integrate some amount of storage in our turbines, we can facilitate the integration to microgrids. But we're not a microgrid system integrator. We can put you in touch with our various partners we have across the globe.
Great. So there are a lot of questions here that are specific, like how can I get a sample file looking at like fuel cell and hydrogen storage? Do you have a database of sample files? How can we use, excuse me, how can we use our currencies? And so on and so forth. So I just want to stop. Unfortunately, we're about out of time. If I see some specific questions here, I'll answer them. But I just want to talk for a minute about how to get your questions answered. So first, we do have a support desk, usersupport.homerenergy.com. I apologize, I don't have a slide on this, but this should all be available through our website. So usersupport.homerenergy.com. You are eligible for support through that during your trial period or after purchase of a license. For students, both before and during your license time, we have success.homerenergy.com, which is a forum, and you can put your questions there, and our engineers do check there occasionally, or you may get other users answering your questions there. There are online videos, there are trainings. We have a short training that is free with commercial licenses for both products. That is about 2 hours long, and where the instructors will do that. We can do a demonstration for you if you're considering purchasing the product. So please send in your questions to our support desk, to our forum. We would love to help you find them. Both products have very long manuals that go into great amount of technical detail, and also ship with quite a few sample files. I do really, as the sort of educational person for the company, I really hear your questions on the sample files, and that is one of my goals for 2019 is to get a bigger library of sample files available to you and a bigger database of sample files available to you. We're also working on really expanding our educational program. So with that, great questions and great answers. I just thought this was one of our best webinars ever. I really appreciate everyone showing up, and want to give Alex and Peter just another minute if they have any last things to say before I end the webinar. Oh, it will be available on our website, so we always do that. So, Alex?
Nothing to add. Indeed, I agree with you. It was very interesting, and I'm glad I got the opportunity to present our technology. And if afterwards there's any more questions regarding our technology or how to use it in Homer, or how we can facilitate your microgrid, please do not hesitate to contact me. My email address is adb@xant.com, so I'd be willing to continue the discussion offline via email.
Great. Peter?
No, I just want to thank everybody for coming, and I think you can see on the slide we're now doing these webinars on a monthly basis, and the next one is going to talk more about Homer Grid, which is a new product, and so many people would be less familiar with it. So just a little plug for thank you for coming for this webinar, and I hope to see you next month at our next webinar, which will focus on modeling grid-connected systems with our new Homer Grid product.
Okay, great. Thank you, everyone.